All right, so we're going to look at algebraic approaches, you guys, which means we're going to start with the bell work and see how well you guys do with algebra. Some of you are not so good because at the first one you were just like, psh, does not exist. No, that is not true. Okay, so the first thing we do, yes, is plug it in. You plug it in and you got that it was undefined, right?
Yeah.
All right, so what do you have to do? Because you don't just go undefined and just be like, oh, it's done. Somebody said it over there, I think. Exactly. I've got to do some algebra, right? I got to expand this, okay? So, if you don't remember how to do that with the binomial expansion, how many of you guys learned it? Anyone? Not enough of you. I'm not going to do it then. So, instead of doing it that way, we will go ahead and just write it over here. So, you can think of it as like 2 plus 3 time. I meant x. I meant x. It's because it's cubed. Sorry, guys. All right, there we go. Sorry. So 2 plus x times 2 plus x squared. Why would I do it that way? Well, because then I can change this to be 2 plus x times, and you're all real good at perfect squares. So you know it's the first term squared plus 2 times them multiplied together, which would be 2 times 2, so 4, plus the last term squared. Then you're going to multiply 2 plus x through. So you're going to multiply everything by 2, right? And now I'm going to go ahead and I'm going to write it over here now. So that's going to be what? 8 plus 8x plus 2x squared. Then I'm going to multiply the x all the way through. So I'll get 4x plus 4x squared plus x cubed minus 8 all over x.
Mr. Bradford, but if we know that x is 0, then why don't we just put x
You
minus
can't.
x minus 8? 8 minus 8.
Because you're going to divide by 0 and you can't do that. What? What formula? The binomial expansion? If you know how to do it, yes. But you were the only one that said you knew how to do it, so I wasn't going to do it that way. Because then I'm going to have to do a mini lesson on that. But yes, you can absolutely use the binomial expansion. All right. So now I have to cancel out the 8s, right?
Yeah.
Which is perfect, because now there's an x in every single term, correct? Okay? So what I'm going to do now is I'm going to take all of these, and I'm going to pull out an x. Maybe I won't do it all at once. I'm going to combine the like terms first. So I'm going to get x cubed. That gets rid of that one. What do we got? 4x squared, 2x squared, so plus 6x squared. 4x and 8x is 12x. All over x. This is still the limit as x approaches 0. Now you can hopefully see, all right, I've got a common term or a common factor of x. I told you before, I'm not going to like actually pull it out again. So instead, I'm just going to change this to 2, this to a 1, and I'm going to get rid of this one to cancel it there. Right? It has to be present in every single term or I can't do it. If that doesn't make sense to you, pull it out as the common factor first. Okay? Then at that point, I've got the limit as x approaches 0 of x squared plus 6x plus 12, and then I just plug it in. Once I plug in what x is approaching, I stop writing limit. So I'm going to get 0, don't need to write it, plus 0, don't need to write it, 12. So it is most definitely not, does not exist.
Okay,
yes?
But I'm a little confused.
Really?
X is equal to 0.
Yep.
Why don't we plug 0 in at the beginning? Like in x.
Well, you can.
X.
The problem is, what do you get? 0 over 0, right?
Yeah.
So I'm going to teach you a way to solve that way faster later, but you don't know derivatives yet. So until you learn derivatives, you can't do it. We have to do it this way.
So Mr. Undefined is correct?
Thanks, sir.
Incorrect.
What?
Undefined is incorrect.
Absolutely, it's incorrect because it's 12. The function is undefined. The limit is 12. So what does this mean, right? Like if we think about what this actually means, if we drew this, right, it means that over here where x is 12, the function's going to be, sorry, not 12, at 0, my bad. Right here, my function's going to exist up here at 12, and it's going to just go like this. Where this point here would be 12, right? It's going to be the point 0, 12. That's what's going on, okay? All right, let's try the next one. I think this one you guys had an easier time with. So the very first thing I do is just plug it in. In this case, that's not going to give me any problems. So I'm going to get e cubed times the cosine of 3 pi over 3, which is really just cosine of pi. What's cosine of pi? Negative 1. So I get e cubed minus 1 or times negative 1. Don't ever leave it like this because somebody's going to write it as an answer of e cubed minus 1. That's not the answer, right? So don't ever leave it like that. Put the coefficients in front and say that. Okay, because as soon as you don't do it, I can guarantee you that one of the times you're going to write it as minus 1. And it's not minus 1, it's times negative 1.
Is there a question in limit?
Yep.
You can't plug in for x.
Of course you can. That's the first thing you should always do. And if it doesn't work, then you got to do some algebra.
How do you know if it works or not?
Well, if it's undefined, you got to then do some algebra.
Also, never is undefined. There is always an answer.
Yeah, it might be that it does not exist, but you're going to figure that out when you put it in, and the two sides go to different things.
Okay.
Okay?
It is never undefined. Maybe there is
Alrighty. So, let's do this algebraic approach, shall we? Well, Anita comes in late and distracts her whole table. All right. So, consider this function. First of all, what kind of function is that? Absolute value. Thank you, Juanita. I think that was you that said it, right? No, it wasn't? Who was it? It was Camila. Camila, thank you. They're in line, so I just heard the voice from that direction. All right, anyway, it's an absolute value. Yeah. The graph of fx is pictured below, so you can see it there. All right, we're going to determine the following limits. Okay? So, first of all, we're going to find f of a using the equation. Not using the graph, using the equation. All right? So, what I'm going to do is plug in what? What am I plugging in here? 0, which is a in this case. You're right that it's a, but a is a moving target because it's 0, 2, and then 10, right? So we're going to plug in 0. So that means I'm finding f of 0, which is going to be 1/2 times the absolute value of negative 2 times 0 plus 4 minus 4. Now we're going to do it in our heads because otherwise we won't have room. Negative 2 times 0, 0. Plus 4, 4. Absolute value, 4. Times 1/2, 2. Minus 4, negative 2. If you need to write that out in steps, by all means do it, right? But at this point, I assume that you're good enough to do that little bit of algebra in your head. All right. Then let's find the limit as x approaches a from the graph. So we're going to go look at the graph at 0 right here. From the left and from the right, what am I approaching? Negative 2. So we're going to answer Benji's question right now. Okay. Now, what about 2 from the right? If it's from the right, how do I plug that in? Do I need to?
What?
I'm just going to plug in 2, exactly. So I'm going to find f of 2, which is going to be 1/2 times the absolute value of negative 2, sorry, not negative, times 2, plus 4, absolute value, minus 4. Perfect. Negative 2 times 2. Negative 4 plus 4. 0. 0 absolute valued. Still 0. Times 1/2. Still 0. We love it. Minus 4. Minus 4. Now let's take the limit. So we're going to approach 2. And we're only going to do it from the positive side, which means I'm going to go a little bit to the right of it and approach it. And I get to, hey look, negative 4.
But
What?
we saw the parentheses first. Or inside.
Well, you treat the absolute value like a parenthesis, yeah. Exactly. All right, so now we're going to plug in 10 to the equation. So we're going to find f of 10, which is going to be 1/2 times, I'm going to just jump straight to negative 20 because I think you can all go negative 2 times 10. It's not, it's absolute value, sorry. Emilio said brackets, parentheses, and messed me up. No, you're fine, man. All right, so I'm going to get negative 20 plus 4. What is that? Negative 16, absolute value. 16 times 1/2. 8 minus 4.
Oh, no, como
What do you think the limit's going to be even though we don't have the graph?
4.
4. Because, and this is kind of like I said, going to what these guys were asking me earlier, right? The very first thing I should do is just plug it in. And I've said it lots. I'm going to keep saying it. Literally, our next lesson is just that. It's just, hey, plug it in. I'm going to give you a flow chart. Which, by the way, I'm not here tomorrow. Sorry, but we'll talk about it. Hey, you finally showed up. Welcome, Carolina. Okay, so when a function is defined and continuous, woo!
Is it always the same when plugging in the function and in the graph?
No,
So why do you say that it equals 4 in the graph?
because most likely that's what we can assume. Now, here's the real reason.
But you're assuming.
I'm not.
No.
I'm not. And I'll tell you why if you read the next statement. I'm not, yes, I guess you could say I'm assuming, but not really. What I'm doing is I'm being analytical. So let's think about the absolute value graph. Is it ever discontinuous? Is there ever a hole in it or an asymptote? No. So therefore it's continuous everywhere, right?
Yes.
So there's no place, there's nowhere that I'm going to have a hole where the function is undefined and the limit could exist. There's nowhere, because the whole thing's like it's defined everywhere for all x's, from negative infinity to infinity. Therefore, this statement's going to be true, right? If it's defined, which absolute value is, and continuous, which absolute value is, then for any x equals a, the limit as x approaches a can be found by simply plugging it in.
Okay.
Right?
It's in absolute value, but in different forms of functions, it's different.
Yeah, that you know.
The key is this. It needs to be defined and continuous. If it is defined and continuous, the very first thing you're going to do is just plug it in and it's going to work. Always. Always. You're going to plug it in and that's just the answer. Okay, so if it's defined and continuous, which you ladies were talking, so you missed it, but like we were just discussing how the absolute value function is defined everywhere, right? From negative infinity to infinity, and there's never any holes or asymptotes, ever. It's defined everywhere. Therefore, f of a will be equal to the limit as x approaches a. Okay? So basically it's like, kind of like a shortcut, I guess. Okay. Boys in the back. Did you hear that? Could you repeat it for everyone? Didn't think so. Pay attention, guys. So in this case, this is a polynomial function. Is a polynomial defined absolutely everywhere?
No.
Yes? Is there any x value that will not work for a polynomial? No, they're always, right? The domain is always real numbers, right? So if it's real numbers, it's defined everywhere, and therefore it's continuous. That means that I can just plug it in, right? So this limit is simply going to be equal to f of 3, right? Because it's continuous and defined. So let's go ahead and do that then. So it's going to be 1/2 times 3 squared minus 2 times 3 plus 3, which means I'm going to get, what is that? 9 halves minus 3. Yep, which will be, hang on, 6, so 3 halves. Okay, I believed you.
No, I know. Either way.
It's all good. Okay, let's look at B. Is B defined everywhere?
Do we have to put it in fractions?
Fractions are better. You could put 1.5, but a fraction is better.
Everywhere and continuous.
Well, we got to use our pre-calc ratings. Guys, what is the one place? I'll give you a hint. It's a rational function. It's not defined everywhere. Where is it undefined? Why?
Because it will give a denominator of 0.
Exactly. So it'll give us a denominator of 0, which means whether it ends up being a point of discontinuity, meaning a little hole, or whether it ends up being an asymptote, either way, it's undefined. Correct? You guys might have called them non-permissible values. Did you guys call them that? That's what you should have done. So we plug it into the bottom, right? 2x minus 3 cannot equal 0, correct? So what I do is I figure out where's that going to happen. Well, 2x cannot equal 3, which means that x cannot equal 3 halves. Are we approaching 3 halves?
No.
No. So is it defined? Is it continuous at that point? Yes. Because it's continuous and defined everywhere except that one point, right? So therefore, we're fine. We can just plug it in. So let's go ahead and do it. This will be equal to f of 3.
Wait, Mr. Bartos, can you explain it more slowly?
Okay, so as we said, we figured out it's not going to be discontinuous at 3. It is at 3/2, but 3/2 isn't 3. So I'm just going to plug it in. So I'm going to get 5 times 3 plus 2 over 2 times 3 minus 3, which I can simplify to be 17 over 3. And so that's my answer. Amazing, right? I think so. All right, so the next one, okay, Camila already identified, yes, it cannot be -1. It's going to have a vertical asymptote. Is 2 -1?
No.
No, 2 is not -1, right? It's not a trick question. No, it's not, so we're fine. But we also need to check that square root, right? Because I cannot take the square root of a negative number. Which values are not going to be allowed on that square root? Well, again, what we can do is we take the discriminant, the thing underneath, and we say that it has to be greater than or equal to 0, right? Okay, so I do that, and that means that x has to be greater than or equal to -2. Is 2 greater than or equal to -2? Yes. Therefore, it is going to be continuous at 2. So I can go ahead and plug it in. It's defined and continuous, right?
I thought square roots could equal 0.
That's why it's greater than or equal to
Yeah,
0.
but why? Or equal to, I thought.
Because the square root of 0 is 0.
It's not, so that's up, exists,
Yep.
that number exists.
Yep. And if you graph it, you'll see that it exists right at 0.
Okay.
It won't exist as soon as it becomes negative. Okay. All right, so let's go ahead and find what f of 2 is then. So it's going to be the square root of 2 plus 2 minus 1 over 2 plus 1. Now, you will notice like there is a negative there. Does it matter in this case? No, the only time that's actually going to matter, you guys, is if it is somewhere where the function's undefined. Because then I need to actually figure out what it's approaching. Okay? But because it's defined, it's going to approach the same thing from both sides. So, it doesn't matter. Okay?
1/3.
All right, so what did I get? Yeah, 4, 2, so I get 1/3, exactly. What was that?
What happens if the x is less than -2? It is undetermined.
Then I mean, the function would be undefined, which means the limit doesn't exist. Okay?
But that will not happen really often.
No, it'll happen. Every once in a while, we'll throw that at you. All right, here is sine defined everywhere. What is the domain of sine? No, that's the one we usually use, but that's a restricted domain. What's the actual domain? If you were to graph sine, what is it?
0 to infinity.
Bigger, even bigger.
Negative infinity.
Negative infinity to infinity. In other words, all real numbers, right? If I graph sine, it's just a wave, right? That's why if you've taken physics, you're going to use sine all the time, right? Because it's how you do all your waves, or cosine, either one. Okay, so therefore, this one is going to be defined and continuous, so we can go ahead, and this will just be equal to f of pi over 2. So I'm just going to plug it in, and I will get sine of 2 pi over 2, which is really just sine of pi. What's sine of pi? 0. So this thing is 0. Cool, right? You guys should circle those. Alrighty. So let's analytically figure out what happens when it isn't defined, right? Because realistically, you guys, that's when limits get interesting. If the function is defined and continuous, you don't even need to take the limit because the limit and the function are equal, right? That's what we basically just, went through. So what we're going to do instead is figure out what's going on when that's not the case. So if we look at this, okay, what happens if we try to evaluate these limits below by direct substitution the way we just did? Well, if I plug in -3 into here, I'm going to get -3 squared is 9 minus 12, right? So -3 plus 3, this goes to 0. If I plug it in here, I'm going to get 9 minus 6 minus 3, that's 0. So I get 0 over 0, which later on you're going to be real excited about. For now, it's annoying because it means we got to factor. Later on, it means you get to do something easy, okay? But we got to learn derivatives first. Okay, so that one was 0. What about this one? If I plug in 1, I'm going to get 1 plus 4 is 5, plus 3 is 8. What if I plug it down here? 1 plus 2 is 3, minus 3, oh, that's 0. That's not so exciting. That one just sucks. And then over here, if we plug in 1, it's going to be the same, right? Does it matter if I plug it in from left or right when I'm just plugging it in? No. So this is going to be the same thing. It's going to be 8 and 0. So what's the problem? They're undefined. They are all undefined. Okay? All of them are undefined. So we're going to have to figure out, what does that mean? Let's go look at it. Okay? So it means that there's discontinuities of some kind at those points, right? That's what undefined means, is that there's some sort of place where the graph doesn't exist. They're either a hole, which is, you know, removable, or jump discontinuity, something like that, or a vertical asymptote. Okay, so it's undefined, as we just figured out, but we're going to figure out that we can still take the limit. So we're going to take the limit here, all right, just by looking at the graph.
What
Okay.
happens if they don't give us the graph, or they need to give us?
I'll show you. That's the next step. Okay, so for this one, we're going to do it easy with the graph because it's easier to understand. So if I approach -3, here's -3. I'm approaching it from both sides. It's hard for me to see what that is, but thankfully, look at that. They told us what it is. What is that coordinate? 1/2. So this is going to approach 1/2. Just is. Okay? What about when I approach 1? That's that vertical asymptote from the left. So when I go here, what am I getting to?
Negative infinity.
Negative infinity. And from the right? Positive infinity. All right, so the function was not existent, right? It was undefined, but the limits all existed. Okay? So that's basically like what our task is going to be here. So in order to figure them out analytically, we had to figure out like where, like with the discontinuities of a rational function, what did you do last year? What did you have to do to figure out? It was like, I can't say that. In Canada, it was the main purpose of your previous class. In this one, it's not. Unless you took Algebra 2 as your previous class. And then it was probably the main focus. You had to factor, right? That's like the goal. Anytime something didn't work, you're like, well, factor it and see, right? So you just kind of factored it and tried to see if maybe something worked out. Why? Because factoring it allowed you to figure out if it was a vertical asymptote or a removable discontinuity. So that's the whole reason we're going to do it. So let's do it. Okay? So we're going to perform that algebraic analysis. We're going to take this and we're going to factor it so that we can hopefully cancel something out, and then we'll be able to figure out what it is. So we'll see how good you guys are at factoring. So the limit as x approaches -3. It's a nice easy one. A is just 1, so it means that we can do this real easy basically in our head. So we need something that adds to 4 and multiplies to 3. That's just going to be 1 and 3, exactly. Then we need to multiply to -3 and add to 2. Well, that's going to be +3 and -1. Yeah?
So there's a whole x minus 3.
Yep. Which is what we just saw in the graph, right? That's what we just saw, that it was a hole at -3. And at -1, because it doesn't cancel out, it's a VA, right? So we know for sure this is a vertical asymptote. This here is a removable discontinuity. Which means the function still doesn't exist, but it's just a hole, right?
So
It's a
removable discontinuity is the same, just means hole.
Yeah, it's just a hole.
Yeah.
Whereas the vertical asymptote means it's that actual line that it cannot cross. Okay? And so now when we take the limit of this, so now we're going to plug it in once we've simplified, we're going to get -3 plus 1 over -3 minus 1, which is going to be -2 over -4, which is 1/2. Exactly what they told us it was earlier, and exactly what the limit was when we looked at the graph, right?
So that's what we do when we don't have to.
Yep. If you don't have the graph, this is what you're going to do. You're going to have to like factor it out.
For example,
For now, don't worry, I'll teach you a trick later.
when the graph doesn't give us the exact coordinate, we do it like this.
Yeah, you gotta do it this way. Or if you just don't have the graph, right? You'd have to do it this way. Okay, so based on our knowledge from pre-calc, we know that a rational function has a non-removable infinite discontinuity. Graphically, a asymptote exists. So that's what we just said, right? That this x minus 1 means there's an asymptote at 1, right? Since the y values do not approach one specific value from both sides at an asymptote, then the limit does not exist. However, we can determine if the one-sided limit approaches -infinity or infinity. Okay? Basically, as soon as it's an asymptote, we know it's going to positive or negative infinity. So really all we need to do is figure out which one. right? We just got to know which one is it going to, which means we get to take some shortcuts here to try and figure that out. So we know that this is an asymptote. We want to figure out, is this going to positive or negative infinity? So what we're going to do is plug in something a little bit to the left. A little bit to the left of 1 would be like 0.9, correct? Yeah? So if I plug in 0.9, it's also easier to use the simplified one, by the way, so that's why you always simplify it first. I don't care what the number is. I'm not going to go and say, oh, this is 1.9 over 0.1. That's not what I care about. I care about the sign. So 0.9 plus 1 is a positive. 0.9 minus 1 is a negative. Positive divided by a negative is negative. Therefore, it's going to negative infinity. Does that make sense? So you can take the shortcut where it's like, I don't care about the number. I already know it's infinity or negative infinity. I just need to know which one. Okay? So if I'm approaching the right, I'm going to do the same thing, but with something bigger. 1 plus 1 plus 1, 1.1, sorry, plus 1 is going to be a positive. One sec, okay? 1.1 minus 1 is also going to be a positive. Positive divided by positive is positive infinity. Was that all you were going to say, or did you have a question?
No, I was like 0.9, and I was going to ask, like, how do we know that the x value is less than 1?
So because this says from the left, we just pick something that's arbitrarily close, but to the left. So 0.9. Yeah, so it's going to equal a point, but that's because then if I go like 0.99, 0.99999, it's going to get close. Yeah. Yep. Okay. Awesome. Any questions, or does that make sense? We're good? All right. So, another algebraic trick. So, graph of this function here, which is a rational radical one, we can rationalize them in order to figure out the limit analytically. So if we don't have a graph, I mean, I gave you the graph, but that's because we're learning. If I didn't have one, I'd have to rationalize it, which again, you should have done in Algebra 2 or Pre-Calc or Math 20, except you guys don't have that curriculum. So, anybody remember what that is? What does it mean to rationalize? All right. So I'm going to take this exactly the same, the one that has the radical, and the only thing I'm going to change is instead of it being minus 2, I'm going to say it's plus 2. And I can't do that, but I can multiply by 1. So I'm going to multiply by a fancy form of 1. Would you all agree that all I did here is multiply by 1? It's an ugly one, but it's a 1, correct? Okay. So, why did I do that? Well, what does this numerator look like now? It's a, like what? What's going to happen to the square root? It's going to cancel. What's going to happen to the middle term when we like FOIL it out? If it's plus and minus 2, it's a difference of squares. It's going to cancel. So the only thing that's going to be left then on the top there, right, is going to be x plus 1, because the square root cancels. The middle term disappears, right, because it's a difference of squares.
Why did you change the x minus 3 to the...
And then it's going to be negative 2 times 2, so minus 4. Right? Yeah? Right? Because I created a difference of squares on purpose to get rid of the radical.
Yeah, why did you change the x minus 3 for the square root?
I didn't. I'm multiplying by it, and now I need to do that. So now I need to show my denominator, which is this ugly thing. Okay? So these two functions are the same. If I were to graph them, I'd get the exact same thing. Which part?
Why would you change the negative to 2 plus 2 when multiplying it?
Because I want the middle term to go away, right? If I have x minus 3 and x plus 3, which is a difference of squares, I get x squared
and you can just do that without it affecting
plus 3x minus 3x minus 9. What happens here? They go away. I can always multiply by 1. And this is a ugly, but 1.
It is not better to have the square root
Right?
on the numerator.
Do you mean another one?
No, wherever it is, I'm rationalizing it. Doesn't matter where it is, I just need to get rid of it. Because I need it to look like this, because now, when I plug, because let's back it up for you, sorry. When I plugged in 3, what happened? I divided by 0. So it's discontinuous. So I had to get rid of that somehow. Algebraically in pre-calc, we would rationalize it, and look, what's going to happen now when we simplify this? Yeah, 1 over it, but yeah. So this numerator is going to simplify down. Actually, we'll keep going vertically. X minus 3 over x minus 3 times our radical. And so those two cancel. This is still there. And so then I'm going to get the limit as x approaches 3 of 1 over the square root of x plus 1 plus 2. Now when I plug in 3, is there a problem?
No.
No. It's still a non-permissible value. We still know the function's undefined. But now we can take the limit. Because this is going to be 1 over the square root of 3 plus 1 plus 2, which is 1 over the square root of 4, which is 2 plus 2, which is 1/4. So this point right here, this hole that exists in my graph, is going to be at the point 3 1/4. So the limit is 1/4. Okay? That's your pre-calc way of doing it. Guys, I'm going to give you easier ways to do it later, but I can't. I have to teach you guys limits and then derivatives, and then we'll come back to this and make it way easier. But unfortunately, I can't yet. So we got to do it our pre-calc way. Okay? Any questions about it, or now are we good? Camila looks scared. All right, let's look at piecewise. Guys, here's the truth. Why do we like piecewise graphs for limits? Why do I'm going to look at a lot of piecewise graphs with limits. Why? Why do you think? Maybe. It's because there's a boundary point where it switches. That's always going to be interesting because we want to know, does the limit exist? Is it continuous? Right? Just like the ones you guys did in that function analysis for me, right? So we want to figure out, does this work? So what we're going to do here, in order to figure it out, is we're going to take this and take a look at the different sides. So let's look at the left first. If I want to approach -2 from the left, which of these two functions am I on, or sub-functions? The first one, right? Because this says when x is less than -2. And if we're to the left of -2, we're up here. So that means that we're going to go ahead and plug it into here. Now it's polynomial. Is it defined? Yeah. So we can just plug it in, right? This is going to be the same as g of -2. So 2 times -2 squared plus 3 times -2, which is going to give me, yeah, just 2. Now, I should back it up a little bit here. Because there's no equal sign there, is the function defined at -2? No, it's automatically not defined because we can see here that this is when x is less than -2. This is when x is bigger. But as we already know, the limit could still exist. And what it's approaching is still helpful for us. So let's now do it from the right side. So if it's the right side, which function am I going to use? The bottom one, exactly. So I'm going to go -1/2 times -2 plus 1. -1/2 times -2 is just 1. 1 plus 1 is 2. I don't even need to do anything on this one now, because now I'm asking for the two-sided limit. If these are the same, it's 2.
So if they are not the same, it's the any.
Exactly. You got it. If those two things are not the same, then Geronimo's right, it does not exist. Okay? Because the left side doesn't equal the right side. All right. So, last thing you're going to do is do this and show it to me. All right?
Only the one at the top. Only that one.
Yep. If you guys at least have this part done, let's go ahead and build those equations. So most of you guys figured out the constraints at least, right? So this one was -3, which means we're going to have when x is less than -3. Okay? And then the one in the middle, the parabola, right? That one's going to go from -3 to 2. Now, can it equal either of those? Yes, it could equal 2 because there's a dot. So I have to put less than or equal to 2. Now the last line here, that one's going to be that x is greater than 2, and just greater, right? Okay, so then let's build the equations. I don't think you need my help with the lines. I'm hoping you can do that, right? Yeah, it's like, we'll do one of them together, I guess. Let's do this first one. What is the slope of this line?
-1.
-1. So this one is going to be y equals -x, and then it's going to be plus or minus the y-intercept. So because this one's so easy, it's probably easiest to just kind of extend it. Oh, it would be -5. Okay? Do the same kind of thing for this one, and you'll get that one. The parabola you might have a little bit of a harder time with, but there's that wonderful form that tells us where the vertex is. Okay? So we write it as x right here, so minus -1, so +1 squared, right? And then -6, because that's where my vertex is. The very last thing that I'd have to check is that there is an a value in front of it. Okay, this is all our pre-calc stuff, right? So this would be y equals, technically there could be like a stretch here, so I would just sort of look at it and see if there's a stretch. A normal quadratic would go up 1 over 1, it does. Over 1 up 2. No, over 1 up.
You don't have to put the y equals because it says f of x equals.
What?
At the start, you don't have to put the y equals because it look.
Oh, you're right, yeah, you're right. So sorry, it would go over 1 up 1, over 2 up 4, over 3 up 9. There's no stretch. Okay, this one has no stretch.
Why the last number is -6?
Because it's the vertex. The vertex lives at -1, -6.
When there is a quadratic, we need to put the vertex, not the y-intercept.
Yeah, exactly. Yeah. All right, and then the last one. Anybody get it yet? What is that? What's the slope?
Y equals -2x
-1.
Minus half.
Close. -1/2 x, and then -1, because it's still going down, right? This way. Yeah. All right. Good work. Now you guys should be able to figure out all the rest of those. Okay. All right. So quickly, just going to go through these 5 types. We did them on the whiteboards, but this way you guys can see the answers as well when you're looking at it. So for this first one, factoring, that one should be very easy. All you need to do here is take everything and factor it. So it's going to be the limit as x approaches -3 of x minus 4, x plus 3 over x plus 3. Those cancel. And then I'm just going to plug it in. So -3 minus 4, which is -7. If you're having a hard time factoring, you got to come see me later, okay? Or watch a different video. Rationalize the conjugate. This is literally the one we did in class, so I feel kind of silly, but that's okay. We're going to multiply this by the conjugate, which is x plus 1 plus 2 over x plus 1 plus 2, which ends up becoming the limit as x approaches 3 of x plus 1 minus 4 over x minus 3 square root of x plus 1 plus 2. Which we know that these cancel because it becomes x minus 3, right? X plus 1 plus minus 4 is -3, they cancel. And then we're just going to plug in 3 for our x, and so we'll get the square root of 3 plus 1 is 4, plus 2, which is 1/4, just like it was in class earlier. All right, then we get into the stuff that's a little more complicated. So when we have a fraction of a fraction, we always need to simplify it into a single fraction, meaning I need that numerator to be a single fraction first, and then simplify it with this. Because, of course, when I plug in 0, I'm dividing by 0. So that's why I need to do the algebra. So for this one, I'm going to multiply it by the fancy form of 1, that is 3 over 3, to get a common denominator. I'm going to multiply this fraction by 3 plus x over 3 plus x, another fancy form of 1. Okay? So when I do that, I'm now going to get the limit as x approaches 0 of 3 over 3 plus x minus 3 plus x over 3 plus x all over x. Now normally, I'm not going to lie to you, you're going to immediately write this as a single fraction because this is, you know, that's what you're doing. I'm doing it in an extra step for you so you can see it. So the limit as x approaches 0 of 3 minus 3, well, those are gone, and then minus x. So it'll be negative x over 3 plus x. And then I would be dividing by x here, which is the same as multiplying by the conjugate. And the reason we do that one is because now these x's cancel. And so then I'm going to get the limit as x approaches 0 of negative 1 over 3 plus x. And then I plug in 0 for my x, and I get negative 1 over 9. Okay. Now, the absolute values, for these ones, if we don't have a graph or anything like that, then what we need to do, and of course, sorry, we plug in 2, we're going to get division by 0. So what we need to do here is we need to look at the two different cases analytically. So we can write this as the limit as x approaches 2 of x minus 2 over x minus 2, or the limit as x approaches 2 of negative x plus 2 over x minus 2. Because the way we analytically look at an absolute value is we flip all the signs saying, well, what if it was negative? So that's what we're doing here, is flipping the signs. Now, when I do this, x minus 2 over x minus 2 is just 1. So I'm literally taking the limit as x approaches 2 of 1, which is just 1. And on this side, it's almost the same, but what I need to do is factor out a negative 1 on top. So this would be the same as the limit as x approaches 2 of negative 1 times x minus 2 over x minus 2. Those cancel. The limit of negative 1 is going to be negative 1. Since those two things are not equal, that means that this does not exist because the two sides are not the same. Okay. And last, we've got a piecewise function here, which is a little bit difficult to read. This is where they're broken. So if we're looking for the limit as x approaches 3, we don't care when it is 3. We're not looking for f of 3. So we need to use the function when x is not 3, which sometimes is two separate functions for left and right. Other times it's just one like this. So for us, we're just going to use the 1. And so obviously this then essentially just becomes a factoring question. So the limit as x approaches 3 is going to be x plus 3 times x minus 3 over x minus 3. Those cancel, which means that it is just a removable discontinuity. And then I can plug in 3 and I get 3 plus 3, which is 6. So the limit of f of x as x approaches 3 is 6. Those are the 5 different cases that the College Board will expect you guys to know. So make sure you do. Make sure you know them.